All right, let's get started. Welcome to 465. I'll spend the first few minutes giving the highlights, administrative highlights of the class, and then I'll jump into the material right away. So we'll be using, well, as always, we'll be using Canvas. Everything that you need is going to be available from the landing page, from the home page. So you can see here, first there's a link to the syllabus, and I require you guys to read this. This is a long document, contains a lot of stuff. And usually when I get questions, administrative questions during the semester, about half the time I answer them by cutting and pasting something from the syllabus. So most of the information is going to be there. But I'll cover some highlights here. Then you have the lecture schedule. So this is going to have it's going to look like this. It's going to contain the lectures that we've done so far, the topics. We're going to put in here the reference to the book chapters, which we're covering. And then there'll be the tentative future lectures as well that are planned. Office hours, you can click here to see the instructor or the TA or the LA office hours. Then for questions regarding the course material, we'll be using CampusWire. So how many of you have used CampusWire before? So some, not a lot. How many of you have used Piazza before? CampusWire is basically like Piazza 2.0, same idea. But Piazza is no longer free, so we switched to CampusWire. So you have to join here with this link and use this code, and then you're in there. And this is really the place. Like if you have questions about the material, we're trying to do in the course, make it as easy as possible for you to get answers to those questions. So one, if you want to see someone in person, we're going to have almost around the clock office hours. I mean, working 10 to 8 every day. We're going to try to have someone available that you can talk to, either a TA or a learning assistant. But if you don't want to do that, you want to just post your question on CampusWire, we'll be checking it. TAs will be checking it at least once a day, often more. So you can really get feedback right away. Then I'm going to be using a digital whiteboard for the lectures, and here I'll have a link where you just click on it and you get the PDF of the notes, of the class notes so far. And it'll be available, it'll be automatically updated. So literally 5 minutes after the class is done, you can see it. So that's pretty much it for Canvas. If we look at the syllabus. Yeah, so this class is going to be co-taught by myself and Professor Stefan Kanzar. I'll be lecturing the first half until spring break approximately, and he'll be lecturing after spring break, so the second half approximately. The recitations are Wednesdays. There's going to be no recitation this week. The textbook is this little guy. You can buy it at the bookstore or Google for a PDF somewhere. We'll, at least for my half of the class, probably 80–90% I'll be following the material in the textbook. So some of the SRT feedback I got last time I taught the class was like, could you create an index of your lecture notes so we know where to look at? I was like, well, that's like, you have the textbook. So if you really want like a polished version of my notes, go to the textbook because it's typed there. It has an index and everything. Notes is just what I'm talking to you in class about. So you can refer to it later for yourself. Grading. So it was brought to my attention in my earlier lectures that this does not add up to 100. So I will fix that, but the relative the idea will be the same. So the homeworks are going to be worth 15% of the final, of the total score. And the final exam will be 35%. And we'll have 3 midterms for a total of 60%. Okay. And these numbers will change. I'll post an updated syllabus. Homeworks, there'll be 10 homework, there'll be homework every week, posted on Thursday and due next Thursday. So we'll have a week to do the homework. And so it's going to be a lot of homework, and the homeworks are designed so that you really practice what's going to be on the exam. The midterms, there'll be 3 midterms and a final. Attendance is required, but for the lectures, I'm recording them and posting them on Canvas. So you'll have it immediately after lecture. It's not a live class. You can't zoom into it to participate if you're not here, but you can view the recording right afterwards. So if for whatever reason you don't want to physically walk into the lecture and want to just watch the video at home, I have no problem with you doing this as long as you kind of keep up with it. I think what often goes wrong if you plan to do that is that you skip things and then you wait, till the homework is due to watch the videos of the lectures the day before, and then it's too late because you don't have time to think about the information. You don't have time to go ask for help or anything like that. So most important thing is you stay on track, whether it's showing up to the lectures or watching them same day. Recitations are not going to be recorded, and they are required for attendance, meaning that there will be material in the recitation which is going to help you do well on the exam. So I may have a question on the exam which kind of follows closely some example you worked through in the recitations. Now the homework policy, the late policy is very strict. So the homework is due 10 p.m. on Thursday. If you turn it in a little late, if you turn it in by midnight, you get 20% late penalty. If you don't turn it in by midnight, you get a 0. And there are no exceptions. So including illness, including serious illness, no exceptions to that. And the reason that is because we want to post the solutions right away. So usually we'll release the solutions at like 12:01 Thursday night. Now, to counter that, we're going to drop 3 of the homework grades, lowest homework grades. So you basically have, 3 times which you can, for whatever reason, mess up or be sick or whatever, and those won't count against you. And that's really a generous policy. We in total number of homeworks is not going to be 15 because the first week you're probably not going to have a homework. Then midterm weeks you may not have homework. So will probably be like 12 or 11 homeworks, and 3 of those you get to drop. Now, we do allow collaborations on homework in groups of up to 3 people. And if you do that, you still have to write your own answer. You have to write your own solution, and you have to write it in your own words, and you have to be able to explain it to a TA if they ask. So this is basically the way the test of whether you followed the collaboration policy or not is if we call you in for a meeting and ask you to explain on the board or whatever a solution that you wrote. If you're not able to do it, that means you didn't really follow the collaboration policy. In that case, you'll get a 0 on the whole homework. So midterms, there'll be 3 midterms. Yeah, and I should say about the homeworks, it's not worth a whole lot of percentage points. It's only 15% of the final grade, but it's a lot of work. There's a lot of homework. The idea is that it's really preparation for your exam. It's a way for you to practice the concepts in the class. And if you're doing the homeworks and thinking hard about them throughout the semester, you're going to be in a great position to do well in the exam. The exams, there's going to be 3 midterms. The first 2, they're all going to be in class. First 2, the dates are already available here, February 9th and March 16th. Again, we have a very strict policy with missed midterms. We are only going to accept university approved. So it means you have a letter from Penn State that says you are in some kind of approved event, like a sporting event or something like that. Those are the only cases where we'll do makeup midterms. On the counter side of that, you will get to drop the lowest midterm grade. So if you do miss a midterm due to illness or something like that, it won't count against you. You can just drop it. So yeah, in terms of communication, at least with me, please don't send me email, use Canvas mail. That way I can keep track of the class communications. If you send me an email, I may not respond to it. Okay, so I think in the interest of time, I want to move on. These are the highlights. Any questions? Yeah. What's this? It varies from year to year. Usually there's a curve. Other questions? Yeah. Midterm is going to have, it's going to be a mix of multiple choice or short answer questions, and usually expect one open-ended question where you have to come up with an algorithm or a proof or something like that. Other questions? Okay, so let's jump into the course material. So the class is called Algorithm Design and Analysis. And that's exactly what we'll be doing. We'll be analyzing, we'll be designing and then analyzing algorithms. Now, to be a little more precise, we're going to be focused on the theoretical study of how to solve computational problems. Okay, so let's break it down. Computational problem, you've seen these, I'm sure. For example, sorting, how to sort n numbers. Okay, the problem is given input of n numbers, output the same permutation of these numbers that is in non-decreasing order. Other examples include finding shortest routes on a map, or scheduling jobs on a server, or answering web search queries. So any of those types of things are computational problems. The other important thing here, word here, is theoretical. There's going to be no programming in this class. Hopefully you have plenty of programming in other classes in computer science or computer engineering. In this class, we focus on theoretical analysis, and I'll talk a bit about why that's important in a minute. We'll be using the word algorithm a lot. So what do I mean by algorithm? It's important to state this at the outset. It's a finite set of unambiguous instructions for solving a problem. There's some key words here. So one, finite, yeah, like if you think of a computer program, it's file of a certain size, certain number of lines. So it's finite. You're not going to have an infinite number of lines in your code. We really won't be worrying about this aspect in this class. The key here, the other key here is the unambiguous part. So here, sometimes you don't need to write down the algorithm in excruciating detail. So we won't even use real code to describe an algorithm. We'll sometimes use plain language or pseudocode, as long as it's clear, unambiguous what your algorithm is doing. Now, an algorithm is correct, right? This is an important notion. If on all legitimate inputs, it outputs the right answer in a finite amount of time. So the key here is legitimate inputs. In other words, if you're asked to sort, like if the computation problem is to sort n positive integers, then it doesn't matter what your algorithms can do, what your algorithm does if it gets a negative number. It can do whatever, because that's not a legitimate input. And so it can be correct regardless of what it does on this non-legitimate input. As long as on the legitimate inputs, on the inputs where it's positive numbers, as long as it's giving you the right answer on that, then the algorithm is correct. So yeah, I've mentioned this before, but we can express algorithm using pseudocode. Pseudocode is like a programming language which you make up that's easy. It's intended for humans to read and understand rather than for the machine to do something. So, I don't care about the syntax of your for loop, whether you use a curly brace or use the do keyword, whatever, as long as I understand what the for loop is doing and where it begins and ends, as long as it's clear to me as a reader, that's fine. So that's the idea of pseudocode. Natural language is another way you can express algorithm. And this is really the most common way we'll use. Well, probably 50-50 with pseudocode and natural language, right? Sometimes it's simple to explain something without having to write the pseudocode. We're not going to be writing actual code in this class. It's too much detail for the purposes of what we're trying to learn. Okay, so we're going to look now. We're talking about what an algorithm is. What do we mean by analyzing an algorithm? There's going to be two things. One, we're going to look at correctness, right? Proving that an algorithm is correct, and runtime, right? Measuring the running time of an algorithm. Now, I just want to point out that there's a lot of other things you can analyze. There are a lot of other things that are important for an algorithm, and especially when you go out into the real world, running time is only one part of it. Other things that are important, for example, readability of your code, modularity, ease of installing it, the time it took you as a programmer to implement it. So yeah, maybe you can get your code to be a little faster if you spend another year working on it, but that's probably not what your company wants you to do, right? So all those other things can be important. However, in this class, we're going to be focusing on correctness and runtime. I just, for the next semester, we're going to be like this, focus on runtime. But I want you to remember, at least at the end of the class, that, okay, that was just one part of the bigger picture. That's going to be important. Even runtime has many facets. So it's a little tricky to analyze runtime. Even, for example, you do a write something to a variable. How long does this take? It depends if the variable is in RAM, or it's on disk, or it's in cache. Those are all going to take very different amount of time. So you can really have analyzing runtime. You can really go into all these kind of details, but in this course, we're going to keep things simple. So we're going to use simple models where we're just like one operation is just one unit of time. Okay. There are more complicated models that you cover if you take graduate courses in theoretical computer science, but this is just an introductory course. So we'll focus just on simple models. We'll also focus on general skills. So I'll talk about this in a second. We're going to be like applying things to specific problems in this class. But really the idea often is not that you've learned something about it, like specific problem, but really about the technique itself, so that when you're somewhere else looking at some other problem, you can apply this technique there. Yeah, so this brings us to the objectives of the course. So first, our classical algorithms, algs, and data structures. And mostly algorithms. We won't spend that much time on data structures. Classical, I mean like sorting problem. Like they're algorithms for sorting problem, which are really crucial in their own right, that you know those algorithms. It's not just the general technique that you want to apply. It's actually just such a basic, such a fundamental computer science problem that you're going to encounter all over the place. So you want to really know algorithms for that problem. Same with data structures. Then analysis techniques. So how do you analyze the running time? How do you analyze the correctness? These are things that you want to, I want to teach you guys the technique, not just how to apply it for a specific problem, but as I mentioned, something more general. And then not just to analyze, but to design algorithms, standard design techniques like greedy algorithms, dynamic programming, divide and conquer. These are techniques that we'll see lots of examples of, and hopefully as you go out into post-graduation, you'll be able to apply those techniques in real life. Well, not in real life, in your job. Okay, so having said all of that, any questions? Otherwise, I have a question for you, which is why? Why study algorithms? Besides that it's required for your major. Nobody has any? Yeah. To better use the hardware and software, yeah. Well, to design better software. Yeah. To maximize the efficiency of the hardware, yeah. Same thing. No. Other thoughts? Yeah. Right, to automate tasks that will be very long to do by hand, yeah. To understand the pros and cons of different ways of doing things, yep. Yeah. To predict what? What are patterns? Yeah, to predict patterns. Yeah. It's fun, yeah. That's true, but probably not for everyone. I'll add a few things to that. So a lot of companies, successful startups and so on, started out because the underlying idea was an efficient algorithm, not like I don't know, some startup that just, I don't know, manages to get to market and everybody hooked on it, but it's not really about some special algorithm. There are startups that really take off because of their algorithm. The best example I have in my lifetime is Google. I think Google was already established by the time most of you guys were using it. In my day, there were many search engines when I started out. And Google just sort of came on the scene, and the reason it beat everybody out, or one of the reasons, it was faster. It was really like instantaneous results, whereas I think Yahoo or what it was, you kind of had to wait for some seconds before you saw results. And that was really the algorithms behind it. And I think the guys that came up with Google are pretty rich now. So that's one example of why I study algorithms. Another very practical example is when you go interview for tech companies, a lot of the questions that they ask you are based on things you learn in this class. Now, this class it's not a prep class for those questions. You'll need to anyway study other stuff in addition, but this is kind of the 50% starting point that you need for those questions. So that's like a very practical reason to study this class. There's something really cool. We won't talk that much in this class until the very end, but there are problems that can be computed efficiently, that can be solved efficiently, and some that are not able to be solved efficiently, at least not that we know of. And so this is areas called computation complexity, studying what problems cannot be solved and which can be solved. And this is kind of cool, and we have public key cryptography is based on results from that. It's really applicable in the world. More generally, computation is fundamental to understanding a lot of the things in the world. Like you can look at biological processes, or the way your brain works, or the way even social networks works through the lens of algorithms. And I think it's sort of more abstract, but having taken this class and learned about algorithms, you'll be able to see things in the world a little bit differently. So hopefully that gives you some reasons to look forward to this class. I want to also tell you a little bit about myself. So I'm a professor here for now 10 years. And I started out graduate school working in theoretical computer science, but I gravitated towards an area called bioinformatics. Bioinformatics is the application of algorithms to solve biologically relevant problems. And I wanted to just give you guys, before jumping into the technical material, give you guys a flavor of some of the results that we had, and show you how algorithms can, like basically used in the medical setting, have an impact there. So this is just an aside. It's not going to be on the exam. So don't worry about that. But okay, so you guys, everybody knows that people, animals generally have a genome, and humans have a genome. It's about 3 billion characters long. It looks something like A, C, G, T, these kind of characters. There's 3 billion of them, and in the human genome. And so for a long time, we sort of knew the human genome, the sequence. Sort of means that still about 10% or so of the sequence was unknown. And just last year, there was a publication that finished the rest of the human genome using algorithms pretty much. I mean, it was a combination of new technologies to like sequence the human genome, but also then clever algorithms to analyze that data and to come up with this with the rest of that 10%. So that's very recent things that are happening, and something that my group and others at Penn State have also done recently is to finish the chromosome Y genome of the human. This is, the chromosome Y is the part that men have that women don't have in the genome. And that part is especially difficult to sequence. And that was still missing even last year. So now we're gonna finish that part as well. So this is a very active area right now of research. Now, we don't all have the same genome, right? We all look different. So these 3 billion bases, approximately 1 in every 1,000 bases differ between any two individuals. And those differences are responsible for the differences that you see. You guys look different, act different, have different, disease phenotypes. That's the part that's medically relevant. So looking at these genome level differences is important medically. So people will take 100 cases and 100 controls, meaning 100 individuals that don't have some disease and 100 individuals that do have a disease, and try to then understand the variations that each individual has, and try to see if there's any variation that's specific to the case, to the disease cohort. And if there is, then you can try to target them pharmaceutically, target those variations. Now, at the level of computers, what's happening is there's something called the VCF file, and that contains the differences that an individual has with respect to the reference. So the file has basically 2 columns, the position and the change. So for example, individual 1 might have in position 3 a change that's delete 2 characters. And individual 2 might have at position 4 delete 2 characters. And here I'm going to reference 0, 1, 2, 3, 4, 5, 6, 7. Okay. So these two these look like they have different variants. But what happens if you apply these changes? So if you apply, remove at position 3, remove 2 characters, you get A, C, G, T, C, A. And if you look at position 4 and delete 2 characters, then what do you get? You get A, C, G, T, C, A. So now if you look at this, you end up getting the exact same sequence. So you can delete at different positions, but still get the same result. And the reason, if you're curious, is that this is a repeat, GT, GT. So whether you remove GT or TG, you're still left with a GT. Now, a lot of software will just treat these 2 variants as being different because the VCF files are different. So what we did with a student about 5 years ago with a PhD student is implemented an algorithm to efficiently identify which variants are the same. And of course, you could just do what we did here, apply them, but that can be very, very slow. It can give us an exponential time algorithm because it's not necessarily one variant is equal to one other variant. It could be a group of variants that if you change is going to equal to some other group of variants. So we had a divide and conquer, efficient divide and conquer algorithm to solve this. And we'll see divide and conquer in basically in a week. Next week, we'll start looking at that. So yeah, that's any questions about that? That's not going to be on the exam, but I just wanted to give you guys a flavor of what algorithms can be used in the real world. Okay, last chance before we jump into technical material. Yeah. How long did it take to come up with the algorithm? Probably the student was working on it probably a year. Yeah, it's not just coming up with the algorithm, it's implementing it, it's testing it on real data, then trying to improve it. So it was kind of an iterative process. It wasn't just like you sit down and you think hard about it and you write out the algorithm. Like, okay, let's try first something naive. Okay, we try it, we implement it, it's too slow. Now let's see what we can do. So it's kind of an iterative process. Okay. Okay, so we're going to start with Fibonacci numbers. This is going to be chapter 0.1 and 0.2 from the book. You guys have, I think you've seen Fibonacci numbers before. Raise your hand. Yeah, great. So just a reminder, the sequence is like this, 0, 1, and then we add the previous two values. So this is 1, 2, 3, 5, 8, 13, and so on. And we'll call this F0, so the 0th Fibonacci number, F1, F2, F3, F4, F5, F6, F7, and so on. Okay, we can write down more formally that the base case that F0 equals 0, F1 equals to 1, and Fn equals to Fn minus 1 plus Fn minus 2 for n greater than or equal to 2. Okay, so these are the Fibonacci numbers. We're going to ask two questions about them in this lecture. One is, what is the size? How big is f of n? And how long does it take to compute it? Fibonacci numbers are going to give us a way to introduce some of the concepts. We'll go into more detail later. So it's kind of an easy example, which we're going to start with. Okay, so first thing I want to do is refresh your guys' memory of improved by induction, because we'll be using that, and it's something you should have covered in 360. So we'll do one claim and a proof. So the claim is that f of n is at least 2 to the 0.5 n for n greater than or equal to 6. Okay, so this answers what is the size of f of n. At least it gives a lower bound on it. Proof by induction. The base case, we have to look at here, and 6. We also need to look at that Fibonacci numbers depend on previous two values. So the base case should have 2, both F6 and F7. Okay, so let's see, F6, what is F6? F6 we have here is 8, and F7 is 13. So let's see, F6 equals to 8, F7 equals to 13. So the question is, for the claim, is it true? We need to show that it's true, that this is more than 2 times 0.5 n, and n here is 6. And here we will need to show that this is greater than or equal to 0.5 times 7. Well, this is 2 to the power of 3, which is 8. So that's true. 8 is greater than or equal to 8. And this is going to be approximately 11.31. you can just plug it into your calculator. So 13 is greater than that, check. Those are the two base cases. Now for the general case, we have for f of n, this is equal to f of n minus 1 plus f of n minus 2. And we want to show that this f of n, right, is greater or equal to the 2.05, 2 to the 0.5 n. What we can do here is use the induction hypothesis to this term and this term. In particular, so the first term has to be equal to 2 to the 0, has to be greater or equal to 2 to the 0.5 times n minus 1. And the second term, it's 2 to the 0.5 n minus 2. So we can, now we are going to try to show this, right? So we want to pull out 2 to the 0.5 n out of there. So let's do that. Let's factor that out. And what are we left with? 2 to the 0.5 times negative 1 plus 2 to the 0.5 times negative 2, which is equal to 2 to the 0.5 n of 1 over root 2 plus this is 1 over 2. And this, if you just plug into your calculator, is more than 1. So you get that this is more than 0.5 n, which is what we wanted to show. All right. So this is kind of this is a review. Doing this, you should have the tools. You should have had from 360 the tools to do this. If you're not sure about something in here, you should really go back and review the 360 material and or come to TA or LA office hours for help with this, because we'll be using induction quite a bit in the class. Now, this is only a lower bound, right? I'll give you kind of the actual value without proof. It's 2 to the 0.694 n. That's without proof. And that's upper and lower bound. So just so we know how fast these Fibonacci numbers grow. Now, this is exponential. This is an exponential function in n. And we'll see that exponential functions are grow very quickly. So the number becomes very large. Okay, now how do we calculate the Fibonacci number, right? Going back to the questions that I posed, what is the size? So we answered that. How long does it take to compute? So let's write down the first algorithm that comes to mind, which is just if n equals to 0, return 0. If n equals to 1, return 1, and otherwise return fib1 of n minus 1 plus fib1 of n minus 2. These are recursive calls, right? So we make 2 recursive calls and we do the sum. When we see an algorithm, this is the first algorithm, right, of the class. When we see an algorithm, we're going to usually ask 3 questions. The first, is it correct? We're going to ask about its correctness. We're going to ask about its runtime. What is its runtime? And we're going to ask, can we do better? So in this case, the correctness is obvious. We just wrote down the definition, basically. So we don't need to prove that. What about the runtime? Runtime is actually, I want to take a second before I jump into runtime. If the question is, how do we analyze running time? If I asked you when you were 18, or let's say when you were starting Penn State, and if you had known anything about programming then or wrote a program, if I ask you, here's a program, what is its running time? What would you have told me? What would you have done? Yeah. Yeah, just run an ID and report the seconds. And you'd probably pick some kind of reasonable input. And you'd tell me, okay, it took 10, here's a sorting program, it took 10 minutes. So what's the problem with that? Why is that sort of not that useful way to measure running time? Yeah. So one is if your algorithm is inefficient, then actually evaluating it can be very slow. Yeah. Some computers have faster hardware. So yeah, hardware, around 10 minutes, but I don't know if you use the Raspberry Pi or the Sun supercomputer, right? So it could mean very different things. Other reasons? Yeah. Yeah, so yeah, it doesn't tell us how the algorithm would work for different types of input. In other words, it's difficult to extrapolate from that one instance to what would happen in other cases. For example, if your input, like let's say we're talking about sorting numbers, if your input is already sorted, it's probably much easier for a sorting algorithm, much faster for it to sort that. I mean, it really doesn't need to do anything, versus if you give it a shuffled, a scrambled input. So it really depends on what is in the input instance. Even more directly, it usually depends on the input size. So did it take you 10 minutes to sort 10 numbers or 10 trillion numbers? Right. Usually for most computational problems, the bigger the input size, the longer it takes. So all these are issues with analyzing running time just by running a program, just experimentally. And that's why we supplement data analysis with the theoretical analysis that we'll do in this class. Now, don't get me wrong, it's still important to do the actual experimental running time. It's because the theoretical analysis also has its limitations. So I'm just saying that experimental analysis is often not enough. We need to do also a theoretical analysis. Okay, so we're going to use theoretical analysis. And we're going to write down the number of steps that an algorithm takes as a function of the input size. We're going to parameterize analysis by size of input, which is usually going to be denoted by n. All right. Now, we mentioned different types of input. Even if you fix n, some inputs are easier to sort than others. So how do we handle that? There are three approaches. So there are three approaches one can think of. One of them doesn't work at all. One of them works, but is very difficult to do. And the third one is the one we'll use in class. So, and that is in fact widely used. So the widely used way to analyze it is worst case analysis. So here T of n is going to be the maximum time or number of steps of algorithm on any input of size n. In other words, the worst case. So I don't care how well you do on the sorted instance. I'm really looking that you, regardless of what the user gives you, you'll be able to do it in that amount of time. Then there is average case analysis. And there is best case analysis. So let's do best case analysis. Let's say someone says, look, why are you so pessimistic? You're looking at the worst case. Let's be optimists. Let's look at the best case. What's the problem with looking at the best case running time of an algorithm? Yeah. Best case analysis, average case analysis. Parametrize. Like to give a parameter, like a function has a parameter. So parametrize analysis by size of input. Yeah. Yeah. Yeah, so you hit really on an important point. It's on several points. So one point is that, I'll put it in a different way. It's possible for you to cheat as an algorithm designer, because you can basically hard code saying, well, if your solution is already sorted, then do nothing and return that solution. If it's not sorted, then here, do something really, really inefficient. But a best case analysis is just going to say, well, you ran on constant time because for the best case, for the sorted case, you already just output what's in the input. And pretty much any algorithm, any problem, you can cheat this way. You can hard code one instance into the algorithm. The second thing you touched upon is that it's not realistic, right? In real life, you don't get the best case. It's true that you also don't get the worst case in real life usually. And that's where average case comes in. So yeah, best case is not used because algorithm can cheat. Give this hard-coded case. Average case analysis says, all right, fine, best case, worst case is not reflective of real life. So we'll just measure, we'll have some distribution on the input. Maybe we'll say it's uniformly drawn at random. And then we'll measure the expected value, the expected running time of the algorithm, the average running time. So this is sometimes used, but the problem is it's difficult to analyze. And not just for the purposes of this class. In general, for professional people, it's still very difficult to sometimes, like mathematically difficult to do an average case analysis. We'll see one example in this class, but otherwise we'll focus on worst case analysis. Yeah. That's one of the problems. It's hard to determine what's average in the sense of, like, what is the distribution of the inputs? I mean, how, like in a real world setting, I don't know, you're looking at shortest paths on the map subject to traffic conditions. Okay, so what's the distribution of traffic? What's the average traffic? I mean, these questions are difficult to model, right? So that's one thing. So even if you say, well, traffic is uniformly random, yeah, that's still not realistic. So to get the correct model there can sometimes be impossible. All right. Okay. So worst case analysis, it is not just for this class, but in general. And the good news is that people have found that worst case analysis usually gives running times that are asymptotically indicative of real world performance. So it's kind of worked out well for computer science over the last 60 years using worst case analysis. Okay, so what is happening with Fibonacci 1 then? Now, this is actually a very simple algorithm. We just count the number of steps. That it takes. So when I run fib 1 of 0, how many steps? And I'll just run t of 0, so the time taken by the algorithm, the number of steps taken by the algorithm when the input is 0. So you do an if statement and a return statement in that case, and you're done. So 2. Same thing for t of 1, you take 2 steps. And for t of 2, or sorry, for t of n, for n greater than or equal to 2, now you do the if statements, and then the addition, and then the recursive calls. So something important here, there's, in this guy, there's some work that's done that's non-recursively. All of this addition, this return is non-recursive work. And then there's some work that's done recursively. So let's write down separately. The recursive work we'll write down in terms of t. So tn minus 1 plus tn minus 2. This is the recursive work done here and here. Then the non-recursive work, it's again the 2 steps, this if statement, and this plus. So that is going to be 3 steps. Yeah. Okay, yeah, so you could say that t of 1 is 3 steps. The point is that it doesn't matter. Okay, the key here is it's a constant number of steps, and we'll see in the analysis that it doesn't matter if you put a 3 or 4. And what else doesn't matter? The reason it also doesn't matter is if you really dig deep into how this is going to be implemented in machine code. This is going to be probably many steps in the assembly code and the CPU instructions. So maybe it's 6 for one, maybe it's 8 for another. We really don't want to start nitpicking these kinds of things. We want an analysis that doesn't depend on the architecture. And that's why we're going to do asymptotic analysis. So we're going to focus on how the runtime behaves as a function of n as n grows. So we don't care if it's going to be n squared plus 5 or n squared plus 10. We also don't care if it's 2n squared or 3n squared. All right, we'll get into that a bit more. But just so you know, that's kind of where we're headed. We don't want to care about these constants. Right, okay, so what we have here is called the recurrence relation. It tells us something about the running time, but it doesn't give us a closed form. Like we don't know if this grows linearly or exponentially or what. We have to solve this recurrence relation. Now in this case, the recurrence relation is easy to solve using what we just did. So this is t of n. I'll just rewrite it here. Recall what fn is. Notice that t of n is greater than f of n because it has the same structure. It's the previous 2 values, right? Like here, the previous 2 values, but you also add a 3. We also add something, whereas here we don't add anything. So this is kind of a neat trick in this case that lets us get out of solving this recurrence relation and just observe its relationship to f of n. And we just showed that f of n is more than 2 to the 0.5 n. So this tells us that the running time is exponential in n. We'll see in a couple of lectures how to actually solve these recurrence relations, from scratch without using these shortcuts. Okay, now exponential time is bad. That's sort of the message, the basic message that I want to communicate. So for example, if you put t 600, this equals to 2 to the 0.5 times 600 equals to 2 to the 300. This is more than the number of atoms in the universe. Meaning that, like, that's the time it takes to compute just the 600th Fibonacci number. And that's more than the number of atoms. So I wouldn't sit around waiting for that job to finish. Yeah. Well, right. So think about the structure. What is this Fn saying? It's a sequence which is the sum of the previous two numbers. Think about T of n is also a sequence. It's also a sum of the previous two numbers and adding a 3. So basically yeah. I think you're onto something. You've noticed something interesting, and to really, you'd need to really do a more full proof to really answer your question. But I don't want to get sidetracked. But that, like, I just want to communicate the intuition here. But yeah, that's a good question. So one reason that exponential time is bad is one way to understand is to think about Moore's law, right? Moore's law tells us that every 18 months the processing speed doubles. Maybe even nowadays that's not true so much, but let's even say that it is. Well, so let's say you wait 18 months. How many more Fibonacci numbers can you compute? If I double the processing time, that I allow, how much larger can I make n? Yeah. Make 1 or 2 more. Yeah. So the reason, so let's say when you add 2 here, you basically multiply what's here multiplied by 2. So you double, if you increase n by 2, you double the running time. If someone speeds up the processor by twice, all you can do is compute 2 more Fibonacci numbers, which is kind of sad. And this is why exponential time is considered very bad, because it doesn't really benefit from Moore's law speedups. Okay, so this brings us to the question now. The third question, you guys remember the third question for any algorithm? Can we do better? Okay. Can we do better? So to understand what's happening, let's draw a recursion tree. So we start with fib1n, and that makes a call to fib1n minus 1, and fib1n minus 2. This one goes to fib1n minus 2 and makes another call to fib1n minus 3. This one makes two calls, fib n minus 3, fib 1 n minus 4. This one makes two calls, fib 1 n minus 3, fib 1 n minus 4, and so on. You can already see something happening here, that fib 1 n minus 3 is appearing 3 times, meaning there are at least 3 separate instantiations where you're going to be computing the n minus third Fibonacci number. Right, and as we draw out this tree, it's going to get even worse. Because, yeah, so you're redoing a lot of computation, and this tells us that maybe you can do better. So the key idea to make it better is to, instead of do this recursively, do this bottom up. So compute the Fibonacci numbers starting from 0 up to n. And that way you can compute every number just once. The function looks like this. This is going to be our second algorithm. So if n equals 0, then return 0. Let's have an array called f of size n, which is going to store the Fibonacci numbers as we're going to compute them. We set the 0th value to be 0. We set the first value to be 1. And then we have a for loop for y equals 2 to n, where we set fi equal to fi minus 1 plus fi minus 2. Notice that both of these values are have already been computed, because our for loop is running from small I to large I. And then we'll have filled in fn, and so we return fn. Okay, so this is our second algorithm. The correctness is obvious. We don't have to prove it, because again, it just implements the formula just in a non-recursive way. What about the number of steps? Well, the number of steps, this is a non-recursive algorithm. That's an important thing to notice right away. Are you dealing with a recursive algorithm or a non-recursive algorithm? This is a non-recursive algorithm. So we're going to write down, we're not going to have a recurrence relation. We're just going to have an expression. So here, let's not even count this time. Let's just say this is a constant number of steps. Right, nothing in there depends on n. This loop iterates n minus 1 times. Inside the loop is a constant operation, 1 step. So then the runtime, let's just be explicit, the number of steps is proportional to n. Which we sometimes say is linear. And we will write, and this is something a notation we'll introduce later, big theta n. We'll introduce this notation later. Next lecture, basically. Now, and there is a caveat here. We'll return to next lecture. But I put the star here so later, when you're looking back at these notes, you remember. Okay. Now, this theta n is much, much better. So this linear time now is much better than exponential time. So if you, for example, double the number, the time that, sorry, if you double the processor speed, then you will be able to compute Fibonacci numbers that are twice as large. So before you could compute 300 numbers, now you can compute 600 numbers. And that's really much better. Okay, so we've analyzed the correctness and the running time. Next lecture, we're going to now focus on this notation and how to use that notation because we'll be using it throughout. That's it for today.